Good day to Dr. Kaur. I am Rishikeshan, son of THANABALAN, matrix number 23131148 from machining course. Today I am going to do my project presentation for my CFD subject, the effect of different velocities and turbulent model of Tesla Model X on the aerodynamic performance of the EV car. The software I use today is SimFlow 4.0. For the introduction, electric vehicle are emerging as a key technology in Malaysia, shift towards a sustainable transportation. So the global environment concerns to grow. Malaysia is positioning itself as a growing market for EV cars. The government incentive and push for reduced emissions. This project focuses on analyzing the aerodynamic performance of EV cars such as Tesla Model X under varying conditions to optimize the energy efficiency and performance. By evaluating the drag force, velocity, and aerodynamic design, the project aims to support the insight that will help Malaysia's transition to a greener and more sustainable market. The main objectives are evaluate the aerodynamic performance of Tesla Model X, the independent factor, three inlet velocities 22, 33, and 44 meter per second, and three turbulent models which is KE, KW, and KWSST. For the next part is the key metrics which is the dependent factor, the output, velocity, pressure distribution, and drag force. And then the research question is how does velocity affect flow and pressure around the car? Which turbulent model provide the most accurate drag and pressure prediction? And what are the key regions contributing to the drag at each speed? And how can these insights optimize EV aerodynamics? For the next part is methodology. As we can see, there is a flow chart for the methodology. Starts from 3D model preparation, create new case, define base mesh, generate mesh, select solver which is simple, set turbulence model, set boundary conditions, velocity and pressure, enable force monitors, run simulation at 200 iterations, monitor residuals and force convergence, plot velocity, pressure and drag force, and then the post-processing. So there are three main steps which is pre-processing, solver and post-processing. For the next part is the simulation in SimFlow. For our project today, there will be 9 simulation based on the combination of velocities and turbulence model as we can see in the table. Each velocity 22.22, 33.33 and 44.44 will be run in all three turbulence models. For the next part is the result table. As we can see, the plotted maximum velocity, maximum pressure and the drag force for each simulation. Now we are looking at the color contours. So for comparing the color contours, I have chosen case 1, case 5 and case 9. So as we can see, the comparison between cases, there are three pictures starts from case 1, case 5 and case 9. Case 1 22.22 meter per second. The color contour show slower flow around the body, especially near the front nose and underbody. And in case 5, 33.33 meter per second, the color contours will show increased flow, speed, and more pronounced acceleration zones around the rear wheel and wheel arch with the transition to faster flow areas. And in case 9, 44.44 meter per second, here the contours will demonstrate the highest flow speeds, particularly around the rear junction and wheel arc as the velocity increases. For the next part is the pressure. Comparison between cases are case 1, 22.22 meter per second. The pressure contour will show high pressure at the nose technician with a clear low pressure wake forming behind the vehicle. And in case 5, the pressure near the nose will be high, but the low pressure wake at the rear will become more pronounced and larger as the flow separation increases. In case 9, 44.44 meter per second, the low pressure wake at the rear will be even larger and more with more pronounced drag due to separation and turbulent flow behind the vehicle. For the next part is the drag force. As we can see, there is a graph plotted here. It's a bar graph of drag force deviation across turbulence models. So there are two types of bar graph here, which is orange and yellow. Yellow is the KW model, and then the orange one is the KWSST model. The KW model shows larger drag force deviation at higher velocities with 104.04 percentage at 44.44 meter per second, which is case 3, and 4.575 at 22.22 meter per second at case 4. For the KWSST model, displays smaller deviation at low speeds, negative 0.997 uh, percentage at 22.22 meter per second, but significantly higher drag at 44.44 meter per second, which is plus 184 percentage. The trend is both models predict higher drag at higher speeds, with KW showing larger increases in drag compared to KWSST. Discussion of analysis. The KE model. The KE model is a stable baseline but underestimates peak values for drag and pressure, making it less suitable for capturing detailed turbulent effect at higher velocities. The KW model is superior for wall-dominated flows, offering accurate result near surface but tend to overpredict drag due to its sensitivity. KWSST model is an adaptable blend reliable across different flow regimes but can overpredict drag under condition of high flow separation, especially at higher speeds. The design focus is to reduce drag, focus on streamlining the rear taper and managing roof trailing edge separation, which help to minimize the turbulent wake and improve vehicle efficiency. And for the last part, we are here for the conclusion and recommendation. The conclusion of the study reveals key insight into how different models, namely KE, KW, and KWSST, affect the accuracy of drag force predictions, velocity distributions, and pressure controls. The KE model serves as a stable baseline but underestimates drag and peak values due to its limitation in handling wall effect. The KW model, while excelling in wall-dominated flows, often overestimates drag due to its heightened sensitivity to near-wall turbulence. The KWSST model provides a balanced approach reliable across via varying flow regimes, though it may overpredict drag under high separation conditions. The recommendations are: optimize rear taper, streamline the rear of the vehicle to reduce turbulence and wake and drag. Manage roof trailing edge separation, improve flow over the roof to minimize the drag and improve stability. Enhance turbulence models. Explore higher order turbulence model for more precise drag predictions. Focus on aerodynamic materials, incorporate lightweight, smooth materials to reduce and improve overall performance. So that's all from me today, Doctor. Thank you.